things out there. Okay, I am going to record, share screen. Take over the screen. All right, should be ready to go here. All right, so we are going to play around with more sums. Oh, I lost my magic pen. All right, so let's take a look at more sums and areas. And so here we'll consider the function, how about f of x equals 4 minus x squared. And we'll look at that on the interval from 0 to 2. It's always a good idea to graph it, either by hand or with a graphing utility. All right, so let's see. Here's somebody in the background. Gerald. Hello, Gerald. Back to this here. Okay, so graph of this thing. We know we have a y-intercept of 4. And if x is equal to 2, we get 4 minus 2 squared, which is 4, which gives us 0. So I have the points at 0, 4, and 2, 0. And given that this is a standard parabola flipped, there's going to be a point over 1, down 1 from the vertex. So put that point in one spot. Do that. Goes right here. There we go. Let's if I label this 4. Oops. There we go. And 2. All right. Point here. So we get this nice, cute parabola. Close enough. All right, and we are going to try and estimate the area in here. So we're going to do that with a bunch of rectangles. So we're going to go for a generic expression for the rectangle. So we're going to go for right-hand endpoints. And we're going to consider the width of the interval if we want to get equally distributed widths. And our width here is the right-hand endpoint minus the left. 2 minus 0 is 2. And we are going to break this up into n chunks. So we're going to say delta x is that total width divided by n. So each little rectangle will have a width of 2 over n. Then we need to figure out what x values we're going to plug into our function, or those the x sub i's. And those, if you're doing the right-hand endpoints, are always your starting endpoint, 0 in this case. And then you add on that width over and over again. You keep jumping to the right, whatever 2 over n happens to be. So we're going to get 2 over n times I, and I is the step I'm at, the rectangle I jump to down the road. So for example, in this picture above here, if I let n equal 4, then what I would end up with is 4 subintervals. And those red lines represent my right endpoints. So my rectangles would look like this. And the last one would have no area because it's going to be flat. And so that's what these formulas help us do for a particular n, and we're just generalizing it. And so now I want to figure out what one of those rectangles looks like, and I'm going to stick it right into a Riemann sum, or sum. A Riemann sum is just some summation that systematically finds rectangles that estimate the area. So I'm going to take the sum. That's my counter I, that counts the rectangles, goes from 1 to n. And the width of one of my rectangles is that 2 over n. My rectangle's base times height, that's my base. And the height is the function value at the given x value, which is right up here. And I can clean that up to just be 2I over n. And my function is 4 minus x squared. And in this case, my x values are those 2i's over n, for a particular number of rectangles n. Could be 4, could be 10. So that's right there is what's called the Riemann sum. The next trick is evaluating. Okay? So for example, we could check that out just for 4. So if n is equal to 4, then that gives me the sum as I goes from 1 to 4 of 2 over n times 4 minus, oops, I'm missing something in my formula. I have to square my x values. And then here I'll have 2I over 4 squared. And then we clean that up and add them up and see what we get. So that's going to be what, I over 2 ultimately. So we can clean that up a little bit more. So that becomes the sum as I goes from 1 to 4, 2 over n. Oh, and it's 4 here. We can clean that 2. Might as well make that half, right? 1/2 times the height of the rectangle, which is 4 minus I over 2 squared, which is I squared over 4. And it looks like we can keep cleaning that up until we're ready to deal with it. So the sum is I goes from 1 to 4. And let's see, what are we going to do? Distribute that 1/2 through there. Half of 4 is, what do we have in there? Half of 4 is 2. And then same thing. Oh no, that's going to be minus I squared over 8. All right, now there's a cool rule of sums that if you have the sum of a difference, you can break that up into the sum of the first part. So I goes from 1 to 4 of 2 minus the sum of the second part, which is I goes from 1 to 4 of I squared over 8. Other cool things that we can do with this is we can say, let's see, if we add up, let's get rid of that. And let's just focus on parts of this. This guy right here just says, take 2, add it to 2, add it to 2, add it to 2. Do that 4 times. So that part is pretty straightforward. That simplifies to just 4 2's added up, 4 times 2. The other one, it's being divided by 8, so I could say that's the sum as I goes from 1 to 4 of I squared all over 8. Every single term is going to have 1/8 in it. So I can just pull that right out. And we have a formula for the I squareds. The formula goes like this. If we sum, let's do a color. If we sum from 1 to n I squared, we went over this in class the other day, that's going to be n times n plus 1 times 2n plus 1 all over 6. In this case, n is 4. So we're going to evaluate that for this sucker right here. So next, we're going to have 4 times 2 is 8. And then minus 8 is in the denominator. And the sum of the I squared is going to be 4 times 4 plus 1, or 5. And then 2 times 4 is 8 plus 1 is 9. And that is all over 6. We can write it like that. So let's see, we can clean up that mess a little bit. 4 goes into 8. Oops, wrong place. Where do we have that? 4 goes into 8 twice, that's better. And 3 goes into 9 3 times, 3 goes into 6 twice, and that's about all I can clean up there. So what do we get then? Now we have 8 minus, what's left in the top, 15 fourths. 8 would be, what, 32 fourths? So my answer is 32 minus 15 over 4. That's a 5, believe it or not. And what's that give me? 32 minus 15 is what, 17 on a good day? This is interesting. I'm all alone doing this. Who's online now? Anybody? We got Gerald still. Hi, Gerald. Okay, back here. Somebody else will join soon. So it looks like the answer is 17 fourths. So 4 goes into 17 4 times, so it's about 4.25 is what we believe the area to be there. If we use 4 rectangles. So I'm just going to double check with GeoGebra here. Let's see, that was my old function. Let's edit that. Get rid of that one. And we'll modify this to be 4 minus x squared. All right, so we're looking for this. Whoa, GeoGebra, settle down. What happened there? My computer's being overtaxed. Hello. Come on, GeoGebra, you can do it. There we go, that's better. And so we're going to do a rectangle sum. Function f, starting at 0, ending at 2, with 4 rectangles and 1 for right-hand sums. And GeoGebra says, yeah, those 3 rectangles, the last one 0, add up to 4.25. So GeoGebra agrees with the result. All right, so we're going to take this a step farther, because that was just for 4 rectangles. Now I got to repeat the whole thing for 10 rectangles and 20 rectangles, trying to get a better estimate of the area. So we're going to back up over to here and take a look at our expression in general right here. So we're going to take that sucker and we're going to try and re-evaluate for n in general. It's going to get a little tricky, but we can hang on to the page. There we go. So we had the sum as I goes from 1 to n. And in that sum, we had a 2 over n times the function, which is 4 minus x squared. And the x's in this case all look like this, 2i over n. So before we clean this up by plugging in n equals 4, here we're going to clean it up, leaving n as n, and see what happens. So what can we do to this thing here? Well, one thing to consider if we look back at the other page, there we are, and if we look over here at the bottom, we were able to, one factor, a property of sums is that if you have a constant multiple in a sum, which I have right here, where I have 1/8, I can pull out that constant multiple. Now, that 8 came from the fact that we let n equal 4. The sum's variable is I, right? So the i's are stuck inside, but n is fixed, right? We're picking some n and going with it from there. So back here, as I'm cleaning this sucker up, I can say that the 2 over n is a fixed constant compared to the summation, so it can be pulled out. So that means my summation cleans up to be just, oops, 10, 4 minus the 2i over n squared. And that would be also written as 4i squared over n squared. Other thing to consider is we can split a sum on a sum or a difference coming inside. So I can break this down again here. So we have the 2 over n hanging out. And then I can say we have the sum of a bunch of 4s. So 4 plus 4 plus 4 n times, minus that 2 over n is still part of the sum, because it has to distribute through the sum as I goes from 1 to n of the 4i squareds over n squared. Now, focusing on this part right here, 4 is constant compared to the variable of the summation I, and n is constant also. So the 4 over n squared can come out too. So rewriting that part, let's go here, switch colors just for fun. Let's see, this sucker right here is just a whole bunch of 4s added up. How many 4s? N of them. So that first part becomes 2 over n times 4n minus, let's see, I'm pulling out the 4 over n squared, and I already have a 2 and an n. So I'm going to have minus 4 times 2 is 8. N times n squared is n cubed. So there's going to be an 8 over n cubed on the outside. And that leaves me on the inside of this last summation just an I squared. Okay. So again, what we did there is we pulled out the 4, highlighter, the 4 and the n squared, and multiplied it by the 2 times 2 over n on the outside. That gives us 8 over n cubed. Now, cool thing here is we know a formula for the sum of the I squareds. All right, so cleaning up further, on with algebra. It's one thing about calculus, it improves your algebra. This is going to clean up because I have n divided by n. That's 1. 2 times 4 is 8. So it's right here underneath. And that's going to give me an 8 minus 8 over n cubed. And then the sum of the I squareds is always n times n plus 1 times 2n plus 1. You'll get used to that formula. Over 6. Okay, so now I'm going to clean up this stuff here. And this we've seen before. It's slightly different form with the 4s. So let's see, the highlighter, 8 and 6 have a common divisor of 2. So about the most I'd want to take this is to say this is 8 minus 4/3 times n plus 1, 2n plus 1, all over n cubed. All right, so given a particular value of n, I can just plug it in and get the sum of all the rectangles. Excuse me 1 second. Okay, I'm back. I had to hush the teenagers a little bit. Okay, so now what we want to do is just take this a little bit farther. If we can find a pattern to those values for n, then we can actually get to the area. So what we want to do here now is we want to know what is the limit as n gets bigger. So I get more and more partitions in there. That means they get narrower and narrower rectangles of my sum. Now my sum happens to boil down to this right here. So the question is, can I come up with a limit for this as n gets bigger? Well, consider the numerator is n times 2n. So that means in the numerator, I ultimately have a polynomial starting with 2n cubed divided by n cubed. And if you remember back from your work with limits in Calculus 1, if you take the limit of a rational function and the numerator and the denominator have the same degree, the leading coefficients are the limit. So that means the limit of this part right here is 2 over 1. So what we're finding is, yeah, there does seem to be a limit to this area. It appears to be 8 minus 4/3 times 2 over 1. And let's check that out some more. So let's see, cleaning that up, what do we get? That's 8 minus 8/3. Common denominator would be 3. So that means I have 24 minus 8, which is what, 16/3? And 3 goes into 16 how many times? 5 1/3 times. So we think that the actual area, after letting those rectangles get thinner and thinner, is 5/3. So let's go check with some computer algebra systems to figure that out. So I could do that in a couple of different ways. I could go over here to this rectangle sum and say, hey, give me 100 rectangles. And with 100 rectangles, I get 5.29. Cool, that's getting closer to what I believe 5 1/3 is the right answer. I wonder if GeoGebra can handle 1,000 rectangles. This might crash my computer. Let's see. Oh, 5.33. That's pretty damn cool. All right, let's take it a step farther. Let's delete or just hide that sucker there and ask GeoGebra another question. GeoGebra can find the area under a curve. The command to do that in GeoGebra is called the integral. And I want integral with f beginning at endpoints. Given my function f, I'm starting at 0 and ending at 2. It says the area is 5 1/3. I'm going to go to Wolfram Alpha as a backup on that. All right, so where's Wolfram Alpha? They are here. Wolfram Alpha understands similar commands. So I can say, hey, give me the integral of the function 4 minus x raised to the second power as x goes from 0 to 2. And Wolfram Alpha is usually pretty good at, if I type it right, graphing it and coming up with an area. So it agrees with all the work that we did. Now, you can get step-by-step solutions, but I think you usually have to buy a subscription to Wolfram Alpha. It's like $5 or $6 a month, or at least that's what it was last year. It's a pretty awesome service. You probably can't use Wolfram Alpha on tests, though. I'll think about that. So, pretty cool stuff we're doing here. Pretty complicated. Let's see, anybody else online? We still got Gerald hanging out. Hello again. All right, so we are playing around with Chapter 5, Section 2. So part of it is getting used to sigma notation. And let's scroll down, show some other things of significance. That's farther than I wanted to go. Oh, where'd they go? All right, so I just lost my place. Load that up. 25 should be good. Okay. So we got sigma notation, and then there's some common sums they give here. We talked about some of these sum rules just now, where we can split a sum on addition or subtraction. Constant multiples pop out, and the sum of a constant is the number of times you try to add it times the constant. Just repeated addition is multiplication. Then we have some formulas. We went over some of these in class the other day for the sum of the first k whole numbers, some of the first k squares, some of the first k cubes. Those are all useful in trying to find limits of our rectangular sums. And we look at the limits in two different ways. One way, and again, these are called Riemann sums that we're building, is we take more and more intervals. As we do that, that forces the width to get smaller and smaller of each subinterval because we're always fixed between a number like 0 and. All right. And then if we then take the limit as those widths get smaller or we accumulate more rectangles, then in the best world, we would find a numerical value or some function value that goes along with that, which is what we're trying to do here. Sometimes, however, we end up with sums that we don't know what to do with. Okay, so let me just show you an example of a sum that's not easily evaluated, that's relatively simple. So, a new example, in which case we have to get another tool to try and analyze this stuff. And So just like in Calc 1, you accumulated all these different tools, like the limit of difference quotient, and then you had all those crazy formulas, and then you learned about taking the derivative of an inverse function to get arcsines and arctangents. We got a whole bunch of work like that to deal with these integrals, these antiderivatives. All right, so let's consider the function f of x equals 1 over x. And for this one, we're going to just look at the interval from 1 to 2. And this is called the reciprocal function. And if we look at a quick graph of this, and let's scale, that's 2, that's 1, that's 1, that's 2. If we take 1 over 1, we get 1. If we plug in 2, 1 over 2 is a half. If we plugged in x equals a half, 1 over a half flips to be 2. And so we get a function that looks kind of like this. And it is asymptotic toward the x-axis, and it is asymptotic toward the y-axis. So one problem here is we can't really start looking for rectangles at 0, because this curve goes up forever. Going up forever is a little trouble for finding the height of a rectangle. And we're not going to be ready to deal with that going up forever with the height of a rectangle till toward the end of the course. So the best we can do for now is just start somewhere after 0. And so for simplicity here, we're just going to say, all right, well, just 1's a nice number. We're going to start looking for area there, and we're going to stop looking at the area there. So we're going to try and estimate the area under the curve here. All right. So to do that, we're going to build a bunch of rectangles. So one easy thing to do would be say, hey, well, we could just do 2 rectangles. And so if we use right-hand endpoints, this would be the first rectangle there, and this would be the second rectangle. That's what's called a lower sum, because each rectangle is below the curve. Oh shit, I can't see anything. Damn it. Ah, there we go. All right, so this is the downside of not having anybody talking back to me in the room or on the computer. Gerald, do you have a microphone? I see yours is muted now. Maybe not. Okay, anyway, let's get back to this picture here. Let me undo a few things. Okay, so we're trying to find the area under this curve between 1 and 2. And again, we could use rectangular sums to do so, which we're going to do. Right-hand endpoint tends to be easier. Left-hand endpoint works fine too. So let's set up a right-hand sum on this sucker. And the procedure is pretty darn similar. We can do a left-hand one in a minute too and see what happens. I need to first look at the width of the whole interval. And so the width here goes from 1 to 2, so that's 2 minus 1, so the width is 1. Then I have to decide how many intervals I want, and I'm going to go for n intervals. N could be 2, it could be 4, it could be 10, intervals. So that means the width of any particular interval, if they're all going to be the same width, uniform, is going to be the width of the whole interval 1 divided by the number of rectangles you want. So it could be 1/2 for 2 rectangles, 1/4 for 4 rectangles, 1/10 for 10 rectangles, and so on down the road. If you're going to use right-hand endpoints, the x values that you're going to plug into the function to get the height of each rectangle will always be your left endpoint of the interval plus your width of each rectangle times I, because you're just accumulating a whole bunch of those widths as you move along. So those are the numbers I'm going to have to plug in to my formula here. So for any one particular rectangle, let's call that delta area. So just a little piece of the area. The width of the rectangle, the base, is going to be 1 over n. And the height is going to be this x value here plugged into my equation. And my equation, if you remember up here, equation is 1 over x. All right, so that's going to be a little messy here. So my height is going to be m 1 over each of those x sub i's. So that's going to be 1 plus I over n. And so then we're going to try and clean this up. And again, we're going to add all those guys up. So then we're going to approximate the area by looking at the sum of a bunch of rectangles. And when we do this kind of sum to approximate areas, that's called a Riemann sum. So I have 1 over n times the height, which is 1 over the x values, and my x values all look like this. Okay, so then we hope to clean this up algebraically, and once we do that, we hope to find a limit. Sometimes we can, sometimes we can't. So let's see what we can do in this case. So I goes from 1 to n, and although I could pull out that 1 over n, I'm going to multiply it through just for fun to see if that helps out, because here I have a complex fraction. And so again, when you're multiplying fraction, you multiply the numerators and multiply the denominators. Well, that's not bad. 1 times 1 is 1. And then in the bottom, I have to multiply, distribute that n through. N times 1 is n. And n times I over n is just I. Well, that simplifies kind of nice. So what's that going to look like? Well, in general, if I is 1, I'm going to have 1 plus 1 over n plus 1, and then 1 over n plus 2. Let's see, I'm running out of room, and that's just going to keep on going. Plus 1 over n plus 3, all the way down the road, up to 1 over n plus n. So for example, if we let n equal 4, I'm running out of room here. Yep. Let's let n equal 4. Then that my formula says that my area would be approximately the sum as I goes from 1 to 4 of 1 over 4 plus I, which would then be equal to 1 over 4 plus 1, so 1/5, 1 over 4 plus 2, 1/6, plus 1/7, plus 1/8. All right, so let's check that out and see what we get. So I'm going to plug that into a calculator and GeoGebra and double check. So new function here. 1 over x. Do it. Just thinking about it. There we go. 1 over x. Get rid of this other stuff. Delete. And I'm going to add a rectangle sum of f, starting at 1, going to 2, with 4 rectangles and 1 for right-hand endpoint. So that's right there. GeoGebra says the answer is about 0.63. Let's blow that up a little more. 28. It's a little bit better. And so I'm just going to double check if I take 1/5 plus 1/6 plus 1/7 plus 1/8. What do I get? I get a decimal. Come on, GeoGebra. And that is incorrect. Uh-oh, I got an error somewhere. Okay, that doesn't match. So where did I make a mistake? Let's go back here. Unless I typed something wrong. Come on, GeoGebra, struggling to exist. Come on, computer, you can handle this. I think I need a new computer. Can't read that. Damn it. Okay. 1/5 plus 1/6 27 plus 1/8. Oh no, that could be right. 533 over 840. Okay, I must have just typed something wrong before. Let's go check GeoGebra with a calculator or Google. 1/5, 6, 7, 8 gives me 0.63. Okay, so our formula does work according to GeoGebra. The problem with this formula here, all right, that sucker. There, is that we do not have any shortcuts for coming up with a single value of that. So there isn't an easy shortcut for 1 over something added up over and over and over again, like there is for the sum of the whole numbers or the sum of the cubes. So we're at kind of an impasse in terms of turning this into a limit that we can evaluate. So my claim right now, page, is that if I want to find the area under f of x equals 1 over x on the interval from 1 to 2, that's a lot of writing. So in math, we came up with a shortcut for all of that. That would be the integral as x goes from 1 to 2 of 1 over x, and then we'll with dx at the end. And this right here is called a definite integral. Okay. And one definition of the definite integral is to take the limits of a Riemann sum as you get more and more rectangles, or consequently as the width of the rectangle shrinks. So in this case, I could write as n gets bigger, which coincidentally forces delta x to get smaller. And we found that our sum simplifies down to I going from 1 to n of 1 over n plus I. However, we have no way to evaluate that. If we try to take n going to infinity and plug it into the denominator there, we get 1 over infinity plus I, which makes no sense. There's nothing we can do with that. So we are kind of stuck. So we need a new technique. So we need a new idea. And so we're going to develop that new idea over the next 2 sections. And part of it revolves around the definition of the definite integral, and also what we need next is called the fundamental theorem of calculus. And that has 2 parts to it. And so we need both parts 1 and part 2 to be able to finish this particular problem. So there's some things that the function seems relatively simple, and we get a relatively simple looking Riemann sum, but we have no algebraic tools to take the limit. So we come to this impasse, new tools needed. All right, so I'm going to stop right here. So the material we've gone over, so we've played around with section 5.1, which is about the idea of using areas and sums together. And then we take that a step farther in section 2, where we use this sigma notation, this sum notation, to be able to write down these patterns of n rectangles. So instead of 4 rectangles or 10 rectangles, we can say, hey, we have n of them. And then we have some tricks that are developed here in order to deal with that. Section 3, which I've hinted at here with the definite integral, is what we're going to continue to explore in class tomorrow. So we should find the homework problems are pretty similar to the stuff I've done here. There's some trig functions I haven't gone over yet. Do your best on those and then email me if you get stuck on them. And I can do some more recordings, or we can do it in class tomorrow. So tomorrow we'll take some homework questions and then take a look at the definite integral. So that's it for now. Have a good day. Do good math. Enjoy all that snow out there. And hopefully school won't be canceled tomorrow so we can see each other on campus. Bye-bye.